Hi everyone, my name is Elvin Hajizada. Thanks for joining today. I will present our recent work titled Interactive Continual Learning for Robots, Neuromorphic Approach. But first I want to thank organizers of ICONS conference and also everyone who contributed to this work, especially our collaborators at Italian Institute of Technology and Technical University of Munich. So let's get going. Today we are going to look into continual learning in the context of robotics and try to propose a neuromorphic solution to this challenging task as a neuromorphic group at Intel. So let's first look into what is continual learning and why is it so crucial. Our modern AI approaches has excelled in many tasks which are generally specific. However, the real-world learning is inherently incremental and open-ended. So let's look into an example of this that is depicted on the right-hand side here. This is actually a picture from a demo we put together with our collaborators at Italian Institute of Technology, where a humanoid robot looks at household objects one by one and tries to learn them incrementally, like in this kind of order. So this is an online learning setting. Because of this kind of sequence of data, we are actually violating one of the main assumptions of deep learning approaches, which is that data should be IID. However, in this kind of learning setting, the training data is actually non-IID. And on top of this, the robot shouldn't forget all the previous objects that it has learned while adapting and learning new objects. However, in the case of standard deep learning, we just try to fine-tune for the new objects. We will forget old objects. This phenomenon is called catastrophic forgetting, and continual learning is trying to address this challenge. There is one standard way of avoiding this in deep learning, which is concatenating new data every time to the old data set that need to be stored all the time and then retrain from scratch. However, continual learning also tries to avoid this, as we want the learning to be continual adaptive. Especially now in the setting of robotics, we also need to be mindful about our resources, like energy, computational resources, time, memory, and etc., depending on the exact robotic platform that we are working on. So the research question we are trying to tackle here is, how can a robot continually and autonomously learn new objects in an online interactive setting from visual input? And we will try to give a neuromorphic answer to this question. For sure, there are modern approaches into continual learning in the modern AI literature. These approaches are roughly divided into 4 groups, first being regularization, where one trains network for the first task, let's say, which can be a single object class or multiple classes. And then we need to look into the weights and try to identify the most important weights for this task. And then we regularize these weights so that in the learning of the second task, this weights doesn't update or move too much. So this way we try to preserve the knowledge of the previous tasks. The second approach is called dynamic architectures, where you add new neurons, nodes, layers, while learning new tasks, so dynamically increasing the capacity of the network. This is going to be roughly the approach that we will take also in our work, but I'm going to talk more about it later. The last two approaches are actually tightly related. These are rehearsal and generative replay. In both of them, We somehow replay old memories while learning new data. The difference is in rehearsal, we store the original images, raw images, and replay them, while in the generative replay, we train a generative network that can generate artificial data from based on old memories. And then similarly, we just replay them. So all is good, but there's one caveat to all this is that these methods are generally applied to standard image classification tasks on standard image datasets like ImageNet. However, there are important differences to the object learning in robotics. So what are these differences? First one is task. Task itself can be different. Let's look at this pictogram, for example. A classic image classification network would classify all of them as a cup or mug, as one category. However, a robot may need to differentiate between different instances of this cup, like if they have a handle or not, for example. The reason is a robot may need to interact with this object, so it's important to differentiate different instances. The second difference is about the data. So standard image data sets like ImageNet has thousands of instances per category, while having only one frame for each instance. So for example, thousands of cups, but only one frame for each cup. While the robot experience is quite different, it may have access to limited number of instances, like limited number of cups, but it may have access to thousands of different frames of the cup or views of the same cup. So I hope this is clear that the data is significantly different between two settings. Generally, also the data collection and labeling itself is very tedious in the robotic setting. So we should make best and most efficient use of our data and labels. Finally, as already mentioned, we will have memory, computational, or energy limitations depending on the exact robotic platform. All in all, we are still lacking an efficient and elegant solution to object learning for robots. So our answer to this question relies on the idea of prototypes. So what are prototypes? These are inspired from cognitive science theories of exemplar and prototype theories. So exemplar theory suggests that human mind stores examples of instances and categories and try to measure the similarity to each new encountered instance and find the nearest one. While this is similar to KNN in AI literature, there is also another theory which says that human mind actually abstracts a prototype from the examples that it encountered, like visually shown here. And the corresponding method in AI is self-organized map and its alternatives, which were first proposed by Kohanen, actually. But why we choose this method for continual learning? So firstly, it's easily interpretable and tractable with prototypes. They lie in the input space as it's shown here, these blue vectors. This is different from standard neural networks where the weight vectors are in a different space, namely they are orthogonal to the decision boundaries that they define. Secondly, the representations is very local with prototypes, as you can see here. So we sample only part of the input or feature space that we have stored prototypes for, while standard neural networks partition the entire feature space into segments. And the network weights are very distributed. Next, we may have adjustable model capacity with prototypes. We can easily increase the capacity by adding, let's say, new prototype vectors. This is tightly connected to what I mentioned previously about dynamic architectures, and this is also what we will pursue. Another interesting feature could be heterogeneous plasticity for prototypes. Namely, each prototype can has its own plasticity level, some of them being more consolidated, some others being more plastic. This may address the stability plasticity dilemma, which is one of the main causes of catastrophic forgetting. Finally, we may have very intuitive unknown class rejections because of the local representation. If an instance appears very far from all of the prototypes, we can easily reject this as unknown class, while in standard neural networks, it's not that straightforward because the entire feature space is partitioned. So any instance would be classified as one of the classes. Importantly, there is also recent interest in combining deep learning with prototype-based approaches. I have put some interesting references here. They generally aim to use deep networks as feature extractor and put a prototype-based learning algorithm on top of these features. Um, Before I forget, also this local representations and adjustable model capacity is also related to the neuromorphic approaches that I will talk about later. So our proposal is also similar to, in a sense that we also combine visual feature extraction and prototype-based classifier in a modular way. This way, we localize learning to one layer, hence we omit backpropagation. Because of this, we can also now implement everything in a fully neuromorphic way. We can utilize on-chip local online learning of our neuromorphic chip. We also connected event-based visual data to our network because that's the most intuitive input modality for a neuromorphic chip to handle. Finally, we augment our learning with a neural state machine to ensure learning autonomy. So now let's look into actually the details of these boxes, modules. So our input data is here. It's a region of interest where the object falls. Then comes the visual feature extraction. We choose a handcrafted simple feature extractor uh, just because we wanted to focus more on the learning side. So this module has one subsampling layer, then 4 Gabor filters with 4 different oriented edges detecting this kind of edges. And then we have the pooling layer. So this is our final features, which is connected to dark blue prototype neurons with plastic synapses. And these are the main synapses where the prototypes are actually stored. The rest of the network, the rest of the neurons are uh, belongs to the neural state machine. Overall, we have only 18,000 neurons and 500,000 of synapses, uh, all put on a single neuromorphic chip. So how is our learning process and what neural state machine actually does? So we implemented on-demand learning, which means only when the user demands learning from the network, the network goes into the learning mode. And this is done by user providing the label to the network for given instance. This way we have interleaved inference and training, and we are now being able to have interactive learning setting. Overall, the learning is divided into 3 possible have three possible modes. First of them being allocation. So I will try to visualize this with a toy example, but bear in mind that this is just only for visualization purposes. Let's say we receive a red class. So at the beginning, we just start and put this, allocate this as um, a new prototype. And let's say we just classify some red instances. We have created, let's say, another blue prototype, and then we receive a blue instance. Because our prototype methods are working based on similarity and proximity measures, this one is classified as red because it's more near to the red prototype. So this is a mistake, which is just judged as a mistake by the user. So it provides the label. This pushed the network into punishment mode, and it pushes the mistaken red prototype away from the instance. Then at the same time, network also boosts the correct the prototypes with the correct labels. So the blue prototypes, this is merging. So we try to merge new instance with the existing prototypes. And if the new inference is correct, then we keep the new prototype there. This way we have superimposed the new instance on top of the old prototype, which made the prototype to move here. Another scenario is also here. Let's say another blue instance appears, again misclassified as red, again punishment, so the red moves away. We try boosting again for merging purposes, but this time all of the prototypes are far from this instance, so it's classified as unknown class. And in this case, we also allocate a new prototype and push the other boosted blue prototype back. So this way, we try to avoid erasing the knowledge about the old data and allocate new resources when needed. So this is all done by neural state machine, uh, which is shown here. It's a rather complicated neural network. You can refer to the paper for more explanation, but shortly, this is the error neurons carrying the error signal to the prototype synapses. This is the synapse for allocating new prototypes, and this group of neurons here helps with the merging. As I already mentioned, we are a neuromorphic research group, so we used our neuromorphic chip Loihi. We implement our spiking neural network on this chip. Loihi chip offers on a neuron level temporal, event-based, and stateful neurons, like uh, biological neurons. On the chip level, it offers parallel, sparse, and asynchronous computation. And crucially for us, it offers learning on fly, which can be configured with the on-chip learning engine. These are some numbers. So each chip has 120K neurons and 128 million synaptic connections. As I said, we connected our chip to the event-based data, as this is the most intuitive input modality. We collected our data in a simulation where a humanoid robot with the simulated event eyes looks at the object, makes a microsaccadic eye movement to see the static objects. And then we change the poses or orientation or the position of the object and record this kind of instances. So this is how the data looks like, different orientations, different objects. We used household objects from YCB database. As I said, we combined the gazebo simulations with eSIM event-based camera simulator. We performed microstatic eye movements to see the static object. So that's this rotational movement you see in the data here. And we made different rotations of the objects to add some variability. To evaluate our framework, we choose 8 objects and 8 rotations per object from our data set. This makes 64 recordings overall. You can see some event frames of Caesar, for example, here. Each recording have 5 microsaccades. 3 of them we use for learning, 2 are for testing, and each microsaccade has some kind of variability, even if it's the same recording. We used our on-demand learning and created the on-demand learning session, a simulated one, where user shows an instance without any label. Network makes the inference. User judge this, and if it's a correct one, it just moves into the next instance, again without any label. Receive another inference from the network, and if it's wrong, if it's judged wrong by the user, which is the case here, this time it provides the same instance. A user provides the same instance with the label. And when the label is provided to network, it automatically goes into the learning mode and comes back with the correct answer this time. So we go over all the training microsaccades in a random order during this on-demand learning session. Then each of these learning sessions is followed by a test session where we don't have any more labels. That's why we don't have learning either. So we just record the accuracy for our testing microsaccades and look into the evolution of the learning. So this is some results. Here we show raster plots of output neurons, label neurons, and error neurons. As I said, we interleaved on-demand learning session with the test sessions in this way. Here we have taken some snapshots from the test sessions shown here. So after first learning sessions, we already reach 88% accuracy on test. And then after the second one, we already reached 97, and then it's converged. Here we can also appreciate the meaning of on-demand learning. As you see, after the second session, there is no more label or error neuron spikes because the network makes most of the time the correct decision, and that's why we don't provide label signals anymore, and there's no more error happening, so there's no more learning actually happening, so it converged. Another interesting result is that our network can automatically allocate resources in an efficient manner. So if the object is simple and has some symmetries, like rotational symmetry, for example, orange, Rubik's Cube, or ball, the network allocate only one prototype for this because they look similar under different viewing angles. But if it's an elongated object like a hammer or screwdriver, then it looks different in different viewing angles, at least to our simple feature extractor. So in this case, the neural state machine allocates more prototypes for this specific object. So we have autonomous resource allocation process here. Finally, we compared our neuromorphic approach to some non-neuromorphic approaches like naive Bayes, passive-aggressive classifier or perceptron implemented in a CPU. So we basically take the extracted features from our experiments and put them through all these classifiers in the same learning scenario. Our classifier performed better than 3 of the methods, and only 1 or 2% less than naive Bayes. But we should bear in mind that naive Bayes is a heavy algorithm, and we also have performed much better in terms of energy, so 300 times better energy per learning instance and up to 150 better for inference instances. So you can see the small energy numbers here compared to other methods. We also have the best execution time for learning an instance, and we are still being on par with the other methods in inference time. And we should note that we actually used 100 time steps for each instance in our neuromorphic chip because of our algorithmic bottleneck. So execution times can be even smaller with some improvements. So to conclude, we proposed a new continual object learning approach for robotic applications where the robots may need to learn new objects after deployment in an incremental setting. We implemented everything in a neuromorphic hardware, and we showed a small scale example, a working one, which can be scaled and made more robust to different variations. I think this can be easily done by improving feature extractor, exchanging it with a deep neural network, for example. However, as every work, we had also our own limitations. Firstly and mainly, we didn't have any weight normalization or voltage threshold adaptation. This is a problem because prototype approaches use similarity measures, and the similarity measure that we have in neuromorphic hardware is dot product. But if we don't normalize it, the non-normalized dot product is not a very good similarity measure. This is well known in the literature. So we try to use punishment mode of learning to compensate for this. But this can actually erase some knowledge, which we try to avoid in continual learning. So in our new work, we are trying to address all of these questions. Another limitation was that we had very simple feature extraction and a very small data set. As I said, feature extractor can be exchanged with the deep network, trained offline, and stay frozen, while we have also the pipeline for generating larger data sets, and we will actually create this kind of data sets in the upcoming works. So that's it for today. Thanks for listening, and please don't hesitate to ask any questions. Thank you.